All right, so here we are with Chapter 2, Elements, Compounds, and the Periodic Table. And so we're going to explore the distribution of metals, nonmetals, and metalloids in the periodic table. We'll look at interpreting chemical formulas. We'll start to understand how to balance chemical equations and how they relate to atomic theory. And more importantly, we'll be using the periodic table. We'll look at how to get the ion charges and how to write formulas and names and compounds for chemical compounds. We'll name name ionic formulas and then write formulas for the chemical names. And then we'll understand the difference between ionic and molecular compounds. This will be the beginning of it because towards the end of the semester, we'll be spending time looking at bonding theories. And last but not least, we'll look at how to name molecular compounds. So just like in the first chapter, I'll try to break these down into about 20-minute segments, looking for good stop points. And so this will be our first segment of this chapter. So the periodic table, well, it basically is going to summarize all the properties of the elements. So again, one of the key assumptions in Chem 150 is that you've had chemistry before, so you know a lot of the basic things, and then we want to be able to expand on those things. And so for the basic things, you should be familiar with your periodic table. Now, I don't want you to memorize necessarily where elements are or what their numbers are, all right? Here we're going to be looking at just how it was put together. So we have the early versions of periodic tables. They started arranging by atomic mass. And of course, most of us are familiar with the name Mendeleev. Meyer might be one you didn't know, but in the same year, these two gentlemen both reported putting together these properties and making a periodic table. This was the groundwork for the basic modern periodic table, which we now use an atomic number. And so we've just listed off the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9. They just keep going. And of course, we know atomic numbers are equal to protons. We then call the rows periods, and the columns are called groups or families. So again, most of this stuff, I would imagine if you're watching these videos, you already know this. All right. So when we're looking at columns, groups, and families, we identify them two different ways. One is to go 1 through 18. This is the standard international way. So it'd be right across the top would be 1, 2, 3, 4, 5, so on and so forth up to 18. The other way is using the A and B's. And this is probably more familiar to some of us, at least growing up with chemistry and being a little older. This was the number one way, and it's still the number one way I think most Americans teach chemistry. And that is we break the periodic table into A's and B's. So we have our group A elements and we have our group B elements. The group B elements, of course, are going to be your transition metals. And so you start off by going group 1A, group 2A, and then we're going to skip all the transition metals and then go 3A, 4A, 5A, out to 8A. So it looks sort of like that, your modern periodic table. So here you can see we have 1A, then 2A, then we skip across to 3A, 4A, 5A, all the way out to 8A. For the international system, you see we go 1, 2, 3, it just goes straight across. You can see it underneath in the parentheses, right? Some family names and group names I need you to know. The very first group going up and down here is called the alkali metals. The second group is called the alkaline earth metals. All of these are called the transition metals. Down here, these two groups, including these two, are called the inner transition metals. Over here we have the last group is called the noble gases, and then group 7A is the halogens. Now we also have the stair-step line, and at this point, if you took a 110 class, or maybe even your basic, high school chemistry, they probably told you metals are on one side, nonmetals are on the other. I know with my classes, I tell them this line is a very definitive line, so you're either here or here. But I also point out to them that at that point, that's a little bit of a lie, but we just don't get into metalloids or semimetals. In this course, you will need to be able to deal with metalloids and semimetals. So we'll need to know that along that stair-step line, elements that are touching that are usually going to be semimetals, which means they have the properties of both metals and nonmetals, and you need to be aware of that. All right, so that representative elements, the main group elements, those are your group A elements. And again, that's going to be the alkali metals was group 1A. These are very reactive. All of them are metals except for hydrogen, but hydrogen actually can behave like a metal. It's just not a metal. It is a gas. They all tend to form +1 ions. They all react with oxygen, and they all form compounds that dissolve in water. When they dissolve, they always make a strong base solution. So they're always going to be basic. And we're going to figure that out when we talk about reactions in a few more weeks. All right. So alkaline earth metals is your group 2A. They are also very reactive. They tend to form the +2 ion. Oxygen compounds are strongly alkaline still, so we still have a strong base when we mix them with oxygen. But these are typically not water soluble. So it makes it a little bit tougher to get them to be bases, if you will, like we think of bases in solution. All right. For your halogens, this is next to the last group. These are also reactive, but they typically form diatomic molecules. And so then, in other words, what we're saying is fluorine will come naturally as F2, chlorine would be Cl2. Bromine is actually a liquid at room temperature, and then the other two are solids, so iodine and astatine. They typically form -1 ions with alkali metals. Now, we're going to see some crazy stuff later on. Like I said, we're going to be looking at bonding theories, and we're going to find out that they can actually use what we call hypervalent states, and they'll make more than one bond. So starting out right now, you really should be really familiar that they make one bond. They have one empty valence electron that they want to accept, and so they typically will form a single bond. But we're going to see some hypervalent stuff later on. Last group is noble gases. These are considered inert, so which means they're very unreactive. So they don't like to react. We know that's based on that octet rule maybe at this point. Only heavier elements of the group react, then very limited. So they don't form charged ions. That's what makes them kind of weird. They are monatomic gases. And once we get past argon, we'll see some of them can actually form compounds as well. Now your transition elements, those are your group B elements. These are all metals. Okay, they're all in the center of the table. They begin in the fourth row, and they tend to form ions with several different charges. Right. So in other words, iron can be +2 or iron can be +3. Copper can be +1 or copper can be +2. Manganese has a whole bunch of options. Okay. Now, when it comes to these charges, we're going to learn ways to figure out what those charges are. So you don't need to memorize what the possibilities are. What we're going to do is use the name and figure out what the charge is for the metal we're dealing with. So don't feel like you have to know that manganese is a 2, 3, 4, 5, 6, or 7. Right? You don't need to worry about that. Again, we'll figure that out in each situation that we're working with. The last three columns all have an 8B designation. Right? Now your intertransition metals at the very bottom of the periodic table, they tend to form +2 and +3 ions. We have the lanthanide series, which are the lanthanide elements. That's 58 through 71. And then the actinide series, which is 90 through 103. Now all the actinides are radioactive, right? So we're probably not going to be messing with those too much, not in this course. Now, you have three options for elements. They can be metals, they can be nonmetals, or they can be metalloids, right? This is your only options here. Now we've organized them obviously by the regions of the periodic table, starting with that stair-step line. Metals, typically on the left side, sodium, lead, iron, gold. Non-metals are on the upper right-hand corner. All right, so that's going to be oxygen, nitrogen, chlorine, elements up in that corner. Metalloids, this is the diagonal, and really it's boron to astatine. So if you look at it sort of like that, the red ones are going to be your metalloids. So even though aluminum is touching the line, aluminum is considered a metal by default. Right? So it behaves like a metal. It has no metalloid properties. Whereas, especially some of you guys who are guys and gals who are in computer engineering, this is going to be where you're going to be operating the most, right in there, right? Silicon, germanium, arsenic, gallium. These are really popular right now for computers. All right, so your turn. Classify the following three elements as either a metal, a nonmetal, or a metalloid. So again, you'll look at your periodic table, and it's simply pick one of the ones that you think is going to be right. So silicon is a nonmetal. Is it a metal? Is it a nonmetal or metalloid? It looks like D is our probably only option. Let's see. Why are they giving respectively? Okay, I was going to say it looked like we had four options here. I was like, that doesn't make any sense. So we have metalloid. So silicon would be a metalloid based upon that last slide. Vanadium would be a metal, but bromine is not a metalloid. So that means none of these are going to be correct. All right, how about strontium is a blank, ruthenium is a blank, and iodine is a blank. So strontium is an alkali metal. No, that's group 1A. Transition metal. No, that's in the middle. Alkaline earth metal. That's 2A. So there we go. That's an option. Then ruthenium is a transition metal. Well, that's true. And iodine is a halogen. So there we go. All right. So let's turn our focus to metals. Most elements in the periodic table are going to be metals. For properties, they typically will have a metallic luster, which means they have a shine or they reflect light. They're typically malleable, which means we can hammer them or roll them out into sheets. They're ductile, which means we can draw them into a wire. They have hardness, right? So some are hard, like iron and chromium. And some can be soft, like sodium, lead, and copper. If you didn't realize, you can actually cut sodium with a knife. And lead, you can easily bend pure lead, right? Copper, you can probably bend sheets of copper, but once it starts to get a little on the thick side, it does start to get a little bit more hard. They all conduct heat and electricity. That's why we use copper actually for wiring, right? They're typically solids at room temperature. In fact, their melting points are usually greater than 25 degrees C, with the exception of maybe mercury. Mercury's melting point is actually minus 39. Tungsten goes way up. It's got a melting point of 3,400. And of course, the reason we point out tungsten is it is the highest. Now, that's not something you have to really worry about, but this gives you an idea of the broad range of what the melting points for metals can be. For chemical reactivity, it's going to vary greatly. For instance, gold, platinum, very unreactive. We use those for jewelry. Sodium and potassium explode in water. So again, not very reactive, all the way to very reactive. For nonmetals, there's going to be 17 elements that are nonmetals. It's the upper right-hand corner. So they exist mostly as compounds rather than as pure elements. And we kind of saw this already. I hinted to the diatomic, right? So fluorine is F2, oxygen is going to turn out to be O2, nitrogen is N2, right? Many are going to be gases. Only the noble gases are going to be monatomic. All of your group 7A is diatomic. Some are going to be solids like iodine, selenium, and sulfur, and phosphorus. You can see have some crazy subscripts there. Looks kind of weird. They form octahedrals, right? Carbon, that's an infinity sign, and that's because carbon actually has 3 allotropes. And hit the next button here, and you can see that we have graphite, coal, and diamond. So depending on the linkages of the carbon, so the carbon is going to form a tetrahedral. We'll see this later in life. And in that pattern of tetrahedral, the longer that pattern goes, that's when you become a diamond. So if you can run your carbon tetrahedral pattern in all 3 directions for a longer series, it forms diamond. If that tetrahedral pattern is only in 1 dimension, or 2 dimensions rather, it makes a sheet, that's going to be your coal, or excuse me, your graphite. And then if it doesn't really run, if it's really haphazard in that pattern, that's when we have coal. Now only one of our nonmetals is a liquid, and that's the bromine, but still diatomic there. So even though it's a liquid, it's still diatomic. So all of group 7A is diatomic. Properties for the nonmetals, they're typically brittle, which means they're going to be pulverizing, they're going to break apart. They actually work as really good insulators, so they don't conduct heat or electricity. And their chemical reactivity, some of those are inert, like the noble gases, but some are reactive, right? So depending on which section, again, it kind of varies, right? Typically, most of your nonmetals will react with metals to form ionic compounds. All right, our last type here, metalloids. There are 8 elements that are 8 elements that are metalloids. They're located on that diagonal line between the metals and the nonmetals. So you have boron, silicon, germanium, arsenic, stilbene, well, tin, beryllium, and then there's the last 2. We don't really work with those 2 at all. Between metals and nonmetals, they have metallic shine, but they're brittle. So again, this is why they're metalloids. They have properties of both the metals and the nonmetals. We use them for semiconductors, and of course, most of you probably know that because they conduct electricity. Not as well as metals, though. right? So silicon and germanium are used to help um, make semiconductors, right? So, your turn. Which of the following statements is correct? Copper is a representative transition element. Sodium is an alkaline earth metal. Aluminum is a metalloid in group 3A. Fluorine is a representative halogen. Or none of these are correct. Right, fluorine is a halogen. That would be right. All of the following are characteristics of metals except they're malleable, they're ductile, they're lustrous, they're good conductors of heat, or they can act as semiconductors. Right, the exception there is they cannot act as a semiconductor. Nonmetals such as bromine and oxygen conduct heat, react with metals, are lustrous, conduct electricity, or act as semiconductors. Right, so they react with metals. All right. I think we'll end this segment here on properties, and then we'll pick up with molecules and chemical formulas. So we'll start to combine these atoms and start to make some compounds. All right, tune in for segment 2.